These are the video notes for section 3.1, which is quadratic functions and models. Models being word problems, so we'll get to that in a little bit. This is the kickoff section to a chapter that really just talks about graphing polynomial functions and rational functions. So functions and their graphs are definitely the focus. We start by talking about quadratic because you guys have a good foundation in quadratic, the graph being a parabola, it's stuff you've seen before. So we can use it to discuss some of the basics, and then that'll take us on into the more complicated graphs and complicated functions. So let's get into the idea of quadratics. Remind you guys of a couple things. First of all, max and min are going to be a big idea for us as we go at least through quadratic and polynomial. And some of the things I want to point out from you guys is the equation, and also talk a little bit about what this book calls this format. So you guys would be used to this form as vertex form, and probably about 99% of the textbooks around there would call it vertex form. For some reason, this one calls it standard. So when you're in WebAssign working on the problem or you see standard pop up, it's actually referring to vertex form. Vertex form being the best for the purpose of graphing, because in that format we have the stuff that we need, which would of course be the vertex, and then also our number out front, which tells us a couple things. If A is positive, our graph opens up. If A is negative, our graph opens down. It also tells us the pattern of change. So something else to remember is what is that? What does it do? We'll come back to that in a second. But back to vertex for a minute. So in this is the vertex, that's h and k, as a coordinate h comma k. It's the location of your max and min. If your parabola opens up, you have a minimum. Now, to be clear on this, the coordinate is not the min or the max, it's the y value. So max and mins are y values, they occur at an x value. So if you're asked to state what the max and min is, you do not state the coordinate, you give us the k, or whatever that y value is at that location. The other thing then is pattern of change, and what pattern of change refers to is how the curve is created. So with, like, for example, with an equation of a line, you got a slope, which is consistent. So when you run a slope, you run the same thing every time, but that's what creates a line. When you're doing a curve, it's not consistent, so I can't say the change is the same, but there is at least a pattern. If the A number is 1, it's a 1 through 5. If A is anything other than 1, then you multiply that number by 1 through 5. And even if it's negative, same thing. So for example, if A is 2, I have a 2, 6, 10 pattern change. Now, how do you use that pattern change? We'll do that in a minute. But with anything that requires you to graph, you look at an equation, and in that equation there should be a way to get the information that would help me. Whether it's like obvious, like a vertex and a pattern change, or we do polynomials later down the road. There's a bigger list of stuff I got to get, but the equation will always help me. It'll always tell me what I need to know to graph. So let's get into, with an actual graph. First of all, this is typically what's called standard form for like every other book out there. So that's what you guys are used to, like ax squared plus bx plus c. This book is calling this not standard form. I'm not sure. It calls it general form, I believe, but we're going to go to vertex form. Now, when I say vertex form, that's what I always call it, but this book is calling this standard. So not trying to make this any muddier for you guys, but this is standard according to this book. And the process of getting from this form to vertex form is complete the square. So, a couple reminders for you guys about that. The first thing we'd have to do is take out the -3, because you can't start completing the square until this has a lead coefficient of 1. Then half the middle term squared, and a counterbalance. Now, you notice that I did +4. Why didn't I do -4? Because what I'm balancing actually is not this number, I'm balancing this number. And this number is -12, so its counterbalance is 12. Also, I'm working on the same side of the equation, so different than in chapter 1 where we were solving and working on opposite sides of the equation, where we would like what you do to one side of the equation, do the other. Well, here it's got to have a 0 effect when you're working on the same side. So if this is -12, +12 will give me the 0 effect. Then comes the rewrite, which is get this down to 2 identical factors, because that's the whole idea of complete the square. And combine your terms, and now we're in vertex form. So at this point, we can start to pull out some of our information. So what is our vertex? What's our pattern of change? So how does the pattern of change work as it popped up there? Well, vertex, of course, you just plot it, and then what you do with the pattern of change is you go over 1 and up or down by the numbers in the pattern of change. Because A is a negative number and my pattern of change is also negative, that means I should be going opening down or counting down. So I go over 1, down 3, over 1, down 9, then 15, I'm off the grid. And I don't need that much to draw it, and I've got my graph. Now, other things that you can find that I don't need to draw the graph are necessary is I don't need the x-intercepts, I don't need the y-intercept. In just about any other graph we'll do going forward, you absolutely do need those things, but because we have unique vertex and pattern change concept that match a quadratic, you don't need to know what they are. But we're going to talk about how you would find them. Y-intercept is, again, super easy. We've talked about that already in the past. That really it's just a matter of letting your x's be 0 because any y-intercept coordinate would be 0, comma, a y value. So the way I get that is by plugging in a 0. So there's my y-intercept, which I just happened to hit with the pattern change also. The x-intercepts are really created by going back to chapter 1 and solving the original equation. In other words, set the vertex form equal to 0 and run through your algebra. So I would subtract 8 divided by 3, take the square root on both sides, and then subtract 2 over, and there's my exact answer. Then for coordinates to plot, I guess I would go ahead and plug into my calculator and give me some points. So now I've got x-intercepts. And again, not necessary to draw the parabola, but again, we're asking you guys to find them, to make sure you know how to find them. And then finally put it all together and see my graph. Domain and range, domain actually for quadratics is a standard all real numbers. There's no domain issues with quadratics. Range, of course, visually depends on, where you see graph. So if I start down here at negative infinity and I track negative to positive, my last y value is up here at the, you guessed it, coordinate of the vertex, right? So what is a max value? A max value or min value, in this case the max, is actually a y value, which in a parabola is the y value of the vertex, also attached to my range. Okay, so in this case we'd say we'd have a max. So graphing parabola is pretty straightforward. Like any kind of graph, as long as you have a good format and you know what's in here and what it tells you, nothing complicated about drawing a parabola. Now, an alternative to having to sketch it or complete the square, if I just want to know vertex, is to do a calculation. So complete the square is an algebraic process. We're going to do a little side step here and talk about how you can just find the vertex. So there's an equation, negative b over 2a, which what that does is calculate the x coordinate of the vertex, and then you have to plug that value back into the function to get its corresponding y value. But basically the idea is the reason I would do this is that I'm not asked to complete the square, change the form of the equation. I don't care about seeing a graph. All I really want to know is where is the vertex, so I can tell somebody what the max or min value is. And sometimes this is actually useful. It'll save you some time. So we're going to just kick into the calculation and see what we got. So we're going to start out with negative b over 2a, which is 9/2. So at this point what I found is the x value of the vertex. Then f of, got to plug this back in and run the numbers. Now, just a matter of you guys taking a few seconds to do the calculation. I'm going to keep it all in fractions here. So squared, multiply, bring my 2 down, get a common denominator, and then put it all together. So now there's a complete coordinate. If I asked you max or min, that doesn't really rely on the coordinate. That relies on me looking at the lead coefficient. The fact that it's negative and my parabola would open down, I know opening down is a max. And then what is its actual value? Right here. So again, max are y values. They're located at the coordinate of the vertex. All right, so that gives you kind of two options. One, I complete the square because I need to change the format, and that's actually nice for graphing. Or two, I don't need to do any of that because I just want to know the coordinate of the vertex for the purpose of deciding what the max or min value is. Well, we're going to transition over to modeling for a little bit. Modeling is word problems, right? And we're going to start by just setting up a model with no additional questions. Then we're going to take a couple where we got to actually set it up and then some questions to follow. We kind of talked about this stuff in chapter 1 with word problems, so I probably won't repeat all that to you guys. We'll just kind of get going. But we'll start out with what you guys are familiar with, which is rectangles, right? We've been doing various rectangular problems. So in other words, let's get our dimensions defined. What's kind of different about this chapter is it's going to tell you to define your function in terms of. So it'll be kind of specific where you won't sort of be just assigning your own variables. But anyways, get it set up in terms of x. So I'm going to call it the height x. And the reason I'm using that for my x is because it says it is 40 feet longer than it is high, which tells me I have to have this so I can compare the length. And so length there is my 40 feet longer than it is high. And then it's a simple function, right? It's the area of a rectangle, so it's basically just length times width, base times height. Also noting that it's quadratic, right? And it's quadratic, and it's going to be a min because this parabola would open up. So if there was additional questions, it would probably have something to do with minimizing something. But for this problem, it's just to go ahead and practice the setup. And we could definitely multiply this out, x squared plus 40x, but in this case, I'm going to leave it just like that. All right, that was just kind of a warm-up. Let's get into the problem where we actually got to answer some questions. So here we are back to our fencing and area style. So here's some perimeter fencing, an area question, which we did some of this early on in chapter 1. But the difference here is instead of having just a rectangular shape, I'm going to divide that area up into 3 smaller areas, which creates more fencing, which creates more things I got to keep track of. So if we're going to write a function that models area in terms of width, then I need to know what my dimensions are going to be. For starters, I don't just have a single width, because I'm talking about this being fencing, I have 4 widths. Anywhere there is fence, I have to count that as material I used. And I need to know that because how do I define the other side? Well, 400 feet of fencing, I just used 1, 2, 3, 4 widths. So I will subtract that and divide by 2. Divide by 2 because it's got to be split equally between this side and this side. So now what I've done is created my dimensions that are w by 200 minus 2w. And of course, that would lead me right to an area function. Now, this is quadratic. It's also a negative 2w squared, which means the parabola opens down, which also tells me my vertex is the location of the max. Most likely there'll be a question about max, so we want to tie the function to the rest of the problem. Like, where is it going? So as I look ahead, it's like largest possible. I know that's talking about max. Okay, so let's get into the cleanup of the function a little bit. I'm going to go ahead and distribute. I am going to complete the square, although I would not have to, right? Because this problem does not require anything in terms of a graph. So I could go negative b over 2a, which might seem easier because really negative b would be negative 200 over 2a, which would be 50. So I guess you might say that's quicker, but just for practice. So factor out the negative 2, half the middle term squared with a counterbalance. And again, I'm balancing negative 5,000, so that would be a positive 5,000 counterbalance. Then go to the rewrite, and then pull out my vertex. Now, if I did negative b over 2a, which gives me 50, and then if I plug 50 back into the original function, I'd get my 5,000. So that, again, may be faster, but again, I just did complete the square so we could practice it. And then we'll get into what the vertex does for us in a second, but now a question about domain. So domain is good to understand in terms of what are the limitations on my problem. In this one, it doesn't have a whole lot of effect on how we answer, but we do want to be clear on when you're working with perimeters, areas, volumes, dimensions, all those ideas, you can't operate in 0 and negative. So low-end domain, which is in other words, what's the minimum my dimensions can be parentheses 0. So we're going to have something. And then what's the upper end? And the upper end actually really is based on the original function. So this is kind of like my 0 as far as the domain goes, but what's the top end here? I can't really go above 100. If I go above 100, that would, let's say it is 100 for starters. If it's 100, that gives me a 0 dimension and zeroes out the area. If I go above 100, it gives me negative and makes my area negative. So my upper limit is 100. So it's good to just reason that out, know what your limitations are. That actually becomes useful when we have to use a calculator. To do the problem, we don't need a calculator for quadratic because we have things like complete the square, negative b over 2a, which does the work for us. Then from my vertex, what is what in these two questions? Well, again, largest possible area. Remember what this actually represents. It's a width that produced an area. So largest possible area is my 5,000 square feet. Again, reminding you guys that a max value is a y value, not the full coordinate. And then the dimensions that maximize that area, well, if this is my width, then I know that this is 50, and then I can plug 50 in and get my dimensions. And then, of course, 50 by 100 ought to produce my total area. So, you know, a geometry-based problem, it's got a quadratic theme through it. Vertex is the focus because the question's about max. And I don't ever need to use a calculator to do much of anything here, and that's actually the point on this one. Now we're going to shift gears for our last problem, talk about where I might need a calculator.